Okay, we are starting 17 minutes late, sorry about it. So there are two parts to this session. In the first one, we'll actually do a high-level overview. And in the second one, we'll be diving a little deeper into some of these concepts. The idea is we'll go breadth first, and then selectively we'll go into some individual pieces. All right? Before we get started, some mindset and principles I wanted to call out. Reasoning is much, much more important than facts. It's very easy in classes to come into a class and listen to somebody else's learning. Okay? That is not what I need you guys to do here. I just now actually gave a recorded statement on camera, just a few minutes back. Facts are going to become more and more easy to look up. Okay? The only thing that we as engineers need to develop is the method of thinking, the method of reasoning. All right? So the way we actually engage in this class needs to require a high level of active engagement from all of you. If you're not doing that, you are just going to be learning, you are just going to be receiving my learnings. It's not you who's learning. Please remember that, okay? So thinking is mandatory. We cannot reason or think without asking questions. So we'll deliberately force ourselves to ask questions, okay? And I'm going to seed some of these questions. I'll strongly encourage you guys to be very, very, very silly when it comes to asking questions. Think about the silliest questions so long as it's relevant to the topic that is on screen, and bring them out when I talk about it. To enforce this, I will lie in this class. Okay? I will lie in this class, which means that if you are not actively engaging, your takeaways are going to be wrong. Okay? I will lie only about facts. Okay? I will not lie about the method of reasoning just to make it easy. Otherwise, we can get into a vicious cycle. All right? When I'm lying about facts, you cannot counter with a looked up fact. You need to counter with reasoning. Because if you look up some fact, I can always concoct some other website with a different fact, isn't it? Right? So the only way we can sort of engage, the only way you can counter my lies is by method of reasoning, okay? So with that, let's focus on why should we invest in understanding internals of things, okay? Imagine there's a web server. This web server uses, so when you make a request, spends 50% of its time in compute, and 50% of its time is actually spent making network calls, disk access, and these sort of things, okay? So, like one of my engineers comes up with a fantastic idea. We need to buy new hardware. We need to buy new CPUs. 10x the speed of the earlier CPU. What is the improvement that I expect on my web server?
Faster.
Yeah, by how much? 10 times? How much? 5x somebody said? 5 times. Actual answer? 1.8x. We increase the CPU by 10 times. And what happened? 1.8x. Anybody who would like to dispute this? Okay. What if the ratio was 40-60? Lesser improvement, right? 1.56x. Clear? Anybody disputing this? Okay. This is what is famously known as Amdahl's law. Okay? It's not very tricky to understand. Actually, let me sort of make it, first present it in a more simplified fashion. Half of the time is actually getting spent on compute, right? So, and half of the time is getting spent there. Infinite improvement on this means that the time taken here goes down to 0. Still half. Which means that asymptotically, what is the number that I can reach? 2x. Make sense? Right? This is a huge law that is equally applicable to hardware and software. When you're thinking about your distributed systems, all of this becomes equally applicable because you've got a bunch of moving parts in there, right? So if you over focus on improving one part, like understand that there would be limits to which your overall improvement happens. So this is what I was describing. Let's save time here. You guys can go through this at your own time. This is what I meant. As improvement goes to infinity, the part that is getting changed comes down to 0. We are still limited by the part that was unchanged, okay? Shows up in different forms. Max gain possible is always constrained by the unchanged part. This also gets phrased sometimes as law of diminishing return. You keep trying to improve one part of it, it's going to give you lesser and lesser returns to it. So the qualifier here is that if you keep changing only one part of it, okay, so the takeaway here is that we always need to think about the system holistically instead of just improving one part alone. And another takeaway from this law is that you're always chasing the next bottleneck, all right? Which means that we need to understand those bottlenecks, which is why we are having this session, all right? Assignment, so I'll, through this session, I'll keep on calling out some assignments. At the end of it, by end of day, there's a list of assignments that will get sent across to you guys. I'm not going to be reviewing them, but for your own learning, I hope that you guys work on it. So assignment is in the 40-60 scenario, what amount of CPU improvement will lead to 80% of max gains possible? Okay, will get sent across to you. Don't worry about taking notes right now. All right, so understanding those bottlenecks is why we need to understand internals, all right? Good engineering, rather great engineering, requires innovative use of resources. The reason earlier I was asking about Nintendo Switch is that if you were to look up what CPU Nintendo Switch uses, what CPU and what GPU it uses, you would be shocked at how underpowered that platform is. And yet, you can play some brilliant games on it. Okay? That requires some brilliant engineering. All right? So, which is why we need to understand internals. Understanding internals gives us a lens to understand a very wide array of programs. Databases, operating systems, network, distributed systems, a very, very large number of things. Understanding their code bases becomes much easier if you understand why those choices were made in those systems. And we'll talk about some of those examples through this session, okay? And lastly, we get better at tech support for friends and family. Like what laptop to buy, right? At least, next time somebody asks that question, you guys would be a little more informed about it. All right, so with that, let's get started with a high-level overview. This is a standard motherboard, right? How many pieces can we identify in this? This one is CPU socket, okay? What else? What else can you guys see? RAM slots, okay? Sorry? PCI slot, okay? Chipset, okay? What else? BIOS chip, yeah, somewhere in there it's going to be there, but difficult to figure out from this. Somewhere it's going to be there, which technically is no more BIOS. It's like UEFI, but yeah. What else can you see? I/O ports, okay. A bunch of input/output ports. What else? Wi-Fi would be somewhere like Wi-Fi antenna would be somewhere baked in this. Yeah. Sorry. SATA connectors, okay, yeah, you can see, I think here, SATA and M2, so it's not very visible, but there's an M2 slot here as well. What else? Voltage regulator, fair enough, not bad. What else? CMOS battery, yeah, we can see it there. All right, so fairly wide amount of information you guys already seem to have. For those of you who are seeing it for the first time, don't worry too much about it. Like I said, facts can always be looked up at any point in time. Sorry, what happened? Okay. Facts can always be looked up. So don't get too worried if you're not able to identify some of these pieces. More important thing to understand is why they work the way they work, which is what we'll spend far more time on. All right? So, let's focus on block diagrams. It's easier to represent on a deck. We've got all of these pieces, right? We've got all of these pieces of components on the motherboard, at least the important ones. Some of the unimportant ones I've left out, but these were the important pieces. Any crucial piece that you think I'm missing? In terms of the interaction with software, focus on that part right now, right? We've got our CPU, we've got memory, we've got some storage of different kinds, right? We've got our GPU card, a bunch of expansion card, and a bunch of IO ports, right? Mota-moti everything is there, right? One of the things that often you guys would have heard is all of these ends up being bundled up as IO, right? So in a sense, we are left with only 3 broad pieces: CPU, memory, and IO. Right? Do you see what is happening here right now? You've blindly accepted. GPU is not an IO? I disagree. Technically it is actually, yes. Yes. The real question is, go ahead.
IO is a part of GPU, but typically GPU does
work of processing, so does this card, isn't it? I can assure you that there is a processor that is actually on this SSD, right? So that cannot be a distinction. So what really makes IO, what really makes some pieces in here IO, whereas some other pieces not so? Why is memory not IO? Sorry? Okay, so when the machine boots up, are you sure that CPU does not get started until memory has been initialized?
No, I say if memory is not idle, then memory is very crucial for the computer.
Memory is very crucial. At least instinctively we feel that memory is very crucial. It's special, correct? Right? But do we just want to rely on our instinct, or do we want to be engineers and we want to think a little better about defining what characterizes IO as distinct from memory? Right? Quickly.
I think it's a primary function of devices.
What is primary function of devices?
Like the IO is responsible for making interaction
With the hardware. One could argue that that's the case with CPU also, no?
It directly interacts with the user. The memory is what the CPU uses to control internally, but the IO things, it gives us output and input.
Okay, so let me phrase it differently. Tell me if that is what you meant. CPU seems to be a little more dependent on the memory, right? It has a special bond with the memory, which is distinct from the IO. IO is largely used for external world interaction or something like that, okay? We are onto something, so one characteristic seems to play out. What else? At a software level, what do you think?
The BIOS won't allow us to start without memory.
BIOS wouldn't allow us to start without memory. Fair enough, along the lines of what the other person was also calling out. Okay, what else? At a software level, think about it. Any other ideas? Yeah.
Maybe it's because because the primary purpose of memory is to just store, and the CPU actually interacts with it by giving it some inputs.
Okay, so memory is largely storage of some kind, and sort of it allows like a buffer zone for the CPU. Is that what you mean?
Like CPU can process everything,
Mm-hmm.
but it can only store a limited amount of data.
So much smaller information here, it needs a buffer zone where it sort of can keep on retrieving from and pumping back to. Is that what you mean?
Yeah.
Okay, fair enough. But one could argue that, that criteria is also met by the disks, by the storage system. Technically, right? So you got to, all right, so in the interest of time, I'm going to make an assertion. Oh, sorry. This part was supposed to be brought, yeah. The assertion is, memory tends, at a software level, memory tends to have a synchronous promise to the CPU, whereas I/O tends to have an asynchronous promise to the CPU. Promise is like it's a contract. Memory has a synchronous contract, okay? When the CPU asks memory something, CPU is not going to move further until that data from memory has been retrieved. If you are doing A plus B, let's say CPU is doing A plus B, the value of A and B would be somewhere in the memory. CPU will need to retrieve it, right? Until then it cannot do the addition, correct? So CPU chooses to not proceed with the instruction until and unless it's actually retrieved the data. Okay? So that is what I mean by synchronous. One could argue that it's the same for disks, for storage, isn't it? Say for example, you want to find the, you want to calculate the checksum for a file. Until and unless you've actually retrieved the contents of the file, you cannot really calculate the checksum, correct? But the difference is, in case of memory, the hardware doesn't inform the software layer. What is the most underlying level software layer running in a computer? Kernel, operating system, right? The hardware does not inform the software that I am waiting for memory. But in case of I/O, the CPU informs the software that, I'm waiting for I/O. That allows the kernel to schedule something else on the CPU while that information is being awaited. That is what I mean by the asynchronous interface. Is that making sense? Yes. Okay. CPU does not inform the kernel, I'm waiting on memory. CPU does inform the kernel, I'm waiting on I/O. Interesting thing is that at a hardware, the reason why I've actually put in mostly is that there are moments when I/O can be exposed out in a synchronous interface, and at a hardware level, memory actually operates asynchronously. Just want to leave you guys with that. We don't have sufficient time to cover why that is the case, but just want to bring it out so that you guys have something to chew on later by yourself. Make sense? All right. If we were to think about it, why should I/O be treated differently? A big reason is, memory is bounded in its behavior, whereas I/O technically is unbounded in behavior, right? I can have a variety of GPU, I can have like a variety of different kinds of ports. Some will give data to me slowly, some will give data to me in a fast way, but memory is always bounded in its promise. Within X amount of time, I'm going to give it to you. Sorry. Within X amount of time, I'm going to give the data to you. So memory is bounded, I/O is unbounded. So this difference of synchronous and asynchronous interface makes sense. All right, I'll let you guys chew on it later. Okay. So we've got three main parts of our computer system: CPU, memory, I/O, and our programs float, or rather interacts in the domain of these three pieces. Okay. Programs that are where largely the CPU is the bottleneck, we refer to them as CPU bound. Programs where largely memory is the bottleneck, we call them memory bound. Programs which are IO bound, like our web server, 4060, do you guys remember? In reality, it's actually far worse off, and we'll do that as an assignment, okay? One thing that we didn't talk about was the connectivity between all of them. Obviously, these are three different, on the motherboard, we actually saw that there were three, these were physically different components, right? Which means that we've got to have some way of talking. That connectivity is super important. That's what we'll talk about as well, okay? So, I'm going to make an assertion, and the rest of the session is going to be going deeper into it. Computer performance is mostly about architecting compute, memory, IO, and connectivity. These are the four broad pieces that we've covered till now, okay? I'm also going to make another assertion. Hardware and software performance is about architecting these. Yet another assertion. All of these can ultimately be distilled down to the concept of latency and throughput. Are these words that you guys have come across in the past? Okay, latency some of you would have. Anyhow, we'll actually cover the definitions of these. For those of you who know about latency and throughput, I'm going to make another assertion. All that matters is latency. Okay? So we'll double click on each one of these pieces. Let's understand latency and throughput. Let's say, I'm very deliberately using a non-technical example here, not because I consider you guys dumb. Okay? I consider you guys super smart. My worry is that if I were to use a technical example, the sheer generality of the concept of latency and throughput would be lost on you. Because you are just so immersed in the technical aspect of latency and throughput, we don't widen our horizons. Okay, that's the reason why so it's not because you guys are dumb, it's because I want you guys to have a much more general view to this concept. Let's say you started a food stall where you are making puris. Okay, so this stall, we have a kadai, or what do you call it, wok in English, right? Where at any given point in time, maximum 5 puris we can actually put in the oil. Okay? Let's say a customer comes in, okay, and orders 2 puris. They cook, it's a one-person stall. The cook goes away from the stall to the behind the scenes setup and starts frying the puri. And let's say that each puri takes 1 minute to fry, okay? In how much time will this person get back the puri? 1 minute, right? Remember, 5 puris max. How many puris did the customer order? 2. So both puris can be fried at the same time, right? So let's look at the latency and the throughput. Latency is from the time that a cause happened and the difference between this to the effect, the intended effect. That delta time is what is known as latency. Okay? So the beginning of this session was 17 minutes latent to the original plan. Okay? So what is the latency that the customer saw? 1 minute. And throughput? 2 ppm, 2 puris per minute. Right? And from a stall's perspective, average latency is again 1 minute, right? And 2 puris per minute. What was the resource utilization? 40%. Why? 2 out of 5, right? The maximum throughput that we could have achieved was 5. Bandwidth of the stall is 5 puris per minute. Okay? So that's another way for us to think about throughput, utilization. Throughput divided by bandwidth. Bandwidth is maximum throughput. Okay? So when you have an internet connection, your bandwidth might be 1 Gbps, but the throughput that you might be getting is lesser than that, which is often the case. Right? Okay. Let's say that, let's consider another scenario. The same customer has come in, ordered 2 puris. This guy, the cook guy goes inside, and just when the cook guy went inside, another person came in. And this guy wants to order 3 puris. Okay? What is the latency for the first person? For the first person is? For the second person, so after 1 minute this guy comes back, that's when this guy ends up ordering, hey, I need 3 puris. I've been waiting for 1 minute already, but now that you're here, 3 puris please. So this guy goes back again, and so what is the latency for the second customer? 2 minutes. Okay? So we are measuring latency can be defined in different forms. You can define it as from the time that I wanted to order to the time that I received it. I can also define it as from the time that I actually ordered to the time that I got it. Okay? Because we are currently interested in the performance of the stall, it makes sense that from the time that I walked in to the time that I got the puri. Make sense? So if we were to think about this, the first customer latency was 1 minute, second customer latency was 2 minutes. Throughput for the first customer was 2 puris per minute, second customer was 3 puris per minute. Average latency is from a stall's perspective. Okay? You are looking at the overall performance of my stall. 1.5, which is the average. 2 people, you can do the calculation yourself separately. Throughput was 2.5. Okay? Utilization was 50%. In the first part, my utilization was 40%. In the second part, my utilization was 60%. Okay? So 50%. All right? So let's say the stall owner recognizes, oh, my customer are waiting just because I'm a 1-person shop. So let me go ahead and hire a person. I will sit directly at the stall and I have a cook who is actually पीछे में. Okay? So anytime that a new customer comes in, I'll just shout out, itna puri aur. Okay? Let's see what happens then. So again, similar scenario, 2 plus 3, the first person came in, ordered 2. The guy at the stall shouts out, 2 puris. And this guy throws in 2 puris and starts frying. Okay? Immediately after that, the second guy comes in, orders 3. This guy is still here because he's dedicatedly managing the stall now. 3 puris. In my kadai, I still had space for 3 more puris, so I threw in 3 more puris. Okay? And this happened just like 1 or 2 seconds later. Okay? What is the expected latency for both the customers now? 1 minute. And throughput is 2 ppm, 3 ppm. Correct? Average latency, 1 minute. Throughput helps hide latency. Okay? But only if you've designed it so. Very important lesson here. All right? Remember that throughput, we didn't change the kadai, did we? Kadai is the same. In the earlier scenario, when we had only 1 person and sort of just moving like this, we had underutilization. Right? 40% and 50%. We had sufficient throughput, but the design of our process was such that throughput was getting wasted. Okay? And when we started utilizing throughput effectively, when we modified our process to start using throughput effectively, our average latency came down. This is what throughput is designed to do. So when earlier we were talking about latency and throughput, that's the reason why I said we care only about the latency. Throughput is just a means to reduce the overall latency. Okay? The same thing will happen when you have a web server. Requests are coming in. Okay? In fact, that's an assignment. The assignment is how can you think about latency hiding via throughput in an HTTP server? A super trivial way to actually handle HTTP requests is that request came in, I'm going to process. Until then, I'm not going to accept any request. I'm going to process because it seems very fast. And then I'm going to return the response. And then I'm going to take up the next request, process, return. Okay, this is a super trivial way to build out the HTTP server. Are you guys noticing similarity with what was happening at this stall? Yes. Right? Okay, so throughput can help hide latency only if we design our system. So if you are not writing software that is really, sort of extracting out the maximum throughput from your resources, you are wasting resources and money for your organization, okay? So the assertion that I'm making is throughput's only purpose is to hide latency. And if you have throughput that is not able to hide latency, it's a design flaw in your system, either at a hardware level or at a software level, okay? So, and another assignment is we've got 7 plus 10. The first customer comes in, orders 7 puris, second customer comes in, orders 10. What is the latency and the throughput? That's an assignment for you. Yet another assignment is you need to figure out 3 examples of latency hiding via throughput. Okay? And try to do as much non-technical as you can, because you really need to internalize this concept. Okay? A few examples I can share top of mind. Please shout out, not me. Please, you guys call out a few examples. I don't want to be the one revealing a few. Non-technical examples, latency, where throughput gets used to hide latency. Or let me simplify it. Let's say where you feel latency and throughput concepts are applicable. Non-technical examples. Restaurants, already covered. Passport services, good. Students asking doubts from teachers, good example. I agree, there's depth to that. What else? Deliveries, yes. Supply chain, absolutely. Absolutely.
Boxing.
Sorry?
Boxing.
Boxing? Boxing, you mean? Boxing? Wow. Okay. I would love to read up an essay on that. So, please try to do a write-up. I would definitely go through it if you do a write-up. What else? Listening to podcast, interesting. Interesting. There seems to be some assumptions in there about the multiprocessing capabilities of the brain, but it's still an interesting concept to explore. There's some part of it that I agree with, subject to some assumptions. All right. I'll give you some other interesting ones. There are engineers who write code in a throughput-centric way, or at least who submit code. PRs, you guys know PRs, right? Pull requests, right? The latency is very high, but so is throughput. One large chunk of code coming your way. High latency, high throughput, right? There are others who are every small change, chuck. There's a PR, right? Title change, PR. Small documentation change, PR. Okay, so latency sensitive engineers are also there. All right, the traffic on the road, right? Fair enough. So you guys think about assignment wise 3 examples of areas where we can hide latency via throughput. All right, so let's come to the last slide before we do a break. So we had all of these components laid out, right? Let's do a very high level overview of how these things talk to each other, okay? If anybody has any opinion on how these things talk to each other, please let me know. How does memory talk to the CPU? Bus. There's something called a bus, right? Okay, so we've got a memory bus which is known as DDR. DDR stands for? Double data rate. Yeah, that's all right. Even I look up these abbreviations all the time, don't worry. Okay, so when I was coming here, I keep on using DRAM all the time, SDRAM all the time, and one just has to look up sometimes. So don't worry about factual issues. Okay, so how does GPU talk to the CPU? Or does GPU talk to the memory and not the CPU? GPU talks to the memory or the CPU? CPU, okay? And via what? Those who built the computers, please speak. PCIe, PCI Express, right? Okay, how many lanes typically? Fair enough. So GPU has something called lanes, okay? So it uses a bus, technically not a bus, but we'll call it a bus for the timing, PCI Express, short for, in short we call it PCIe, okay? 16 lanes, which means 16 such links. Each link for PCIe version 4 is, each link is 16 Gbps. Remember, this is small b, that is capital B. Difference? Bits versus byte, okay? Here, latency was 0.1 nanosecond. Bandwidth was 25 gigabyte per second. Here, latency is 100 plus nanosecond. And bandwidth you can calculate, right? So let's reduce this down to 2 gigabyte approximately. We'll talk about why it's approximate later. So 2 times 16, 32 gigabyte per second is the bandwidth that is potentially exchangeable. Bandwidth, not throughput, okay? All right, so what else? What are some of the other pieces? All of these other pieces, remember, for GPU to be able to speak to CPU, whatever this PCI Express thingy is, CPU needs to be able to understand it, isn't it? Otherwise it cannot speak PCI Express, right? We've got a bunch of other different kinds of equipment. We've got USB, we've got Ethernet, NVMe, SATA. Do you really think CPU should have all of this understanding? Because for every new protocol that we build, we will need to then put it into the die of the processor. Should the CPU bear all of that headache? It will come at a cost, right? So one of the things that we often do is that we have a chipset. Those who read through the spec, the consumer class CPU, how many PCI Express lanes did it have? It's not a memory test. Please look it up right now and quickly tell me. Anybody? Fastest finger first. I thought I had requested some of you to keep it open. 16? 20 lanes, right? Server class CPU had how many? 80 lanes. Wow, 4x difference, huh? Right? So if consumer class CPU has 16 lanes, because remember these are physical links, right? So it's not like you can, this is something that is configurable in software. Physically, those transistors need to be, built out into, sort of etched into the CPU, right? So the number of lanes are fixed. All depends upon now how we actually make use of it. One of the big reasons why chipset is also used is expanding the total number of lanes that are available. Okay? One is obviously, building additional kinds of protocols. And yet another is expanding the total number of lanes. Okay? For example, this one is a by 4 lane. That's a by 4 lane. This is a PCIe card, 4 times 100 Gbps. So 4 ports of 100 Gbps. Remember, bits, gigabit per second. Okay? So this is a network card. That's a SSD. Both of NVMe is a protocol built on top of PCI Express. Okay? So we've got chipset providing all of these extra functionality. Obviously, the chipset will need to speak to the CPU as well, right? That bus is called DMI. Okay, Intel calls it DMI, AMD calls it UMI, some other manufacturer might call it whatever, PMI, does not matter. Okay, what matters is that there's an interconnect. Okay, for what it's worth, every single time I do this, for Intel's I remember, AMD's I always have to look up that, okay, what is the bus called? Okay, principle is the same. All right, how many lanes? How many DMI lanes? 8, maximum 8. Now DMI electrically is identical to PCIe. Okay, so it's essentially effectively the same 16 gigabit per second per lane is what is actually going in. So if the chipset is providing far more I/O, all of that I/O is being shared over those 8 lanes. Do you understand why GPU would want to be having its own highway now? If it didn't have its own highway, what could happen?
Its performance will be limited.
Its performance would be limited. Because this can get congested depending upon how many things you've actually plugged downstream. Make sense? Right? There would be contention. Right? Okay, so based on this, tell me where are the lies? What are the lies I have said here? Oh, we are just over time. Quickly, yeah, go ahead.
Sir, first you were telling that GPU uses PCIe and telling us that it directly connects to the CPU.
Yeah.
But the NIC card which you have shown also uses PCIe, but it goes through chipset.
Yeah,
So,
that's possible.
but a motherboard contains PCIe slot similar to each other, but it doesn't have a specific PCIe slot for graphics.
So it's not that motherboard actually has a dedicated graphics slot. It's called as such, but what it really has is a dedicated by 16 lane slot. So every physical slot that you see has X number of lanes, sort of wired into it. Okay. So the slot that is meant for graphics card has 16 PCIe lanes wired into it. That part is accurate. Go ahead. Yes.
And the PCI card connects to the chipset to the CPU through a very congested line. How the speed is 10 gigabits?
How is it?
How the speed is more than the GPU?
So this is, no, speed is, okay, you make an interesting point. So this is 4 times 100 Gbps, right? 400 would transfer 50 gigabyte per second, right? And I'm making it go via, fairly, so 4 lanes would provide me how much bandwidth? 8 gigabyte per second. 2 gigabyte per second per lane times 4, 8. Whereas how much do I need? 50. So forget about this. Yahin par break ho jayega na, right? Okay, good. You found the first issue. So 4 lanes can support 4 times 1 Gbps port, but certainly not 400 Gbps ports. They are just not, forget about this, congestion to hai, but even the main connectivity to the chipsets itself is actually broken, right? There is no possible way that a 4 times 100 Gbps NIC is going to be pluggable on a by 4 slot. Make sense? Okay, what other lie? There's one more lie. Huh? Yeah.
The number of lanes are 24 actually, but the maximum supported are 20.
That is correct. And which means that this lane is oversubscribed. And this is actually fairly normal. The expectation is oversubscription ratio, the way you would think about it is, not all of these things are going to be operating at 100% throughput all the time. Okay? So it's like our roads. If roads cannot be designed for the whole city to be out at the same time, correct? There's some oversubscription ratio that we actually run with. Same is the case here as well. Okay? So, that is my reasoning. But good that you identified that there's oversubscription. What other lie? Look at it carefully. There is like something staring at us in the face. GPU latency? 100 plus nanosecond. It should be less. It is a very good point. I was going to pose that as a question, but why does GPU have memory of its own usually? Yes. If it didn't have it, then it would have to go through this 100 nanosecond and plus 0.1 nanosecond to actually reach here every single time. Correct? Which would really choke it up. So the point is, by having memory here, it chooses not to be bothered by this. This latency is actually directly PCI Express latency. Because, question is, why have I represented these lines instead of, and while this one is a thick sort of a thing that I've, that's a bus. What do you mean by that? Asynchronous? That I've already called out. That doesn't explain why I should have like a thick one versus thin lines. Quickly, guys.
That transfers more data at a time.
Fair enough. Let's park this. You heard.
Maybe these are 16 different lanes to pass on the data simultaneously in different way, and these are only one.
This one is only one. Okay, fair enough. This point we'll cover, but I was just responding to why, to one of the questions. We'll deal with the why this is thick and why these are thin lanes separately. One more lie before we break, quickly. SATA disk has a connector, right? This is a different kind of connector, SATA connector to the chipset. And then chipset converts those into PCI Express commands and sends them up. Okay. Look up the latency of memory quickly. Latency. Look up the latency of memory right now on your. How much should it be? Not all of you were approaching this session with an assumption that Amod may lie. Please assume that I would be lying. Okay? Latency should be higher. Why should it be higher? Like I said, looked up fact cannot be a reason. Sorry? Synchronous in nature, which means that latency should be lower. If I'm relying on you to give data back to me, my expectation is you're going to be bloody fast. Right? So from that perspective, 0.1 nanosecond actually makes sense, expectation wise. You were saying something, somebody over there? Okay, oh yeah.
So the memory is sending like 25 GB per second. That's a lot of throughput. So it should also require a lot of latency as well. Like the request example we said, since we had a lot of data.
So that's an interesting point. You observed that with high throughput, usually higher latency, but that's data that you're extrapolating. There is absolutely nothing that we've discussed till now which mandates that high throughput should come with high latency. One of the reasons why we'll discuss why this is fat, okay, is to allow for high throughput without high latency. Speed of light, what is it? Okay. Speed of signaling on a wire on a PCB substrate. Okay, that thing, hard surface that you actually see. That is, let's assume that it's the speed of electrical signaling is half of the speed of light. Okay, it varies a little depending upon the PCB substrate, but if it is half, it means that it is 1.5 times 10 to the power 8 meters per second, right? Which means in 1 nanosecond, how much distance is it traveling? In 1 nanosecond, 0.15 meters, which translates to 15 centimeters, right? So if in 1 nanosecond, 15 centimeters, 0.1 nanosecond would mean 1.5 centimeter. Do you really think on that diagram that I showed, all these slots were 1.5 centimeter away? Right? Reason. There is your reason why it cannot be 0.1 nanosecond. Okay? What should be the latency? 15 seconds? 15 nanoseconds. 15 or 50? 15. Okay, very good point. We'll talk about it. Latency is 50. Yes, you looked it up, isn't it? Yes. Yeah. So,
Actually checking the difference between DDR4 and 5.
yeah,
DDR5 latency is more than DDR4.
we'll talk more about those after the break, okay? So these were the two lies, a bunch of questions. Remember the principles? We want to ask questions. Is DMI part of, we talked about DMI lanes being like, this is electrically PCI Express. So when we talked about 8 lanes of DMI, is it in addition to the 20 lanes that the CPU was offering? Or is it a part of it? Food for thought. And if you were to want to find out, how would you actually find out? Food for thought, not for immediate discussion. Would the chipset add latency? So if this direct line was 100 nanosecond, would this chipset, when it is downstreaming PCI Express, would this add latency? Food for thought. Why is everything other than memory those single lines? We touched upon it. We'll go into detail a little later. Assignment. How would you think about bandwidth needed to drive an 8K monitor? Don't remember all of this. I will send it to you textually. 8K monitor running at 60 Hertz, assuming RGB pixels. So 3 pixels, 8 by each, so 24 bits per pixel, being transferred at 8K resolution at 60 Hertz. How much bandwidth would be needed? And from that, calculate how many lanes of PCIe 4 would actually be required. Okay, starts giving a, the reason why I'm asking you guys to think about all of these calculations is, the reason why I asked you, the reason why I'm lying, what this guy actually called out here, 4 by 100 Gbps. These are things that, you know, if as engineers we get into the habit of doing double checking with multiple different angles to the same problem, opens up a completely different way of looking at things. Okay, so that's all. We'll take a break and okay. So DDR SDRAM. Memory is something that all of us are quite familiar with. We should actually be able to get to this quite quickly. What does RAM is something that we understand, right? What does random access mean? Silly question. Huh? It is not sequential. You can look up any part of it, correct? So can you in a hard disk?
No, actually in a hard disk, we have to rotate one.
That is if it is a rotating magnetic disk, right? So technically, technically SSDs are actually random access, isn't it? You don't have to access, you don't have to go through X amount of data before you reach the address that you wanted, right? Okay. D. Dynamic means what? Food for thought, think about it. S. I looked it up before coming here. So you know what you guys should be saying right now? Amod, why are you questioning us about facts? Didn't you say that facts are less relevant? Why is nobody telling me that? All right. So S is synchronous. Okay. Effectively, what that means is that there is something about this interface that is synchronous. Remember that memory and this thing, IO thing that we talked about, right? What is that synchronous thing? Let's see if we get to that. DDR. What does that mean? It should mean something. Data is transferred in 2 channels. Don't worry about guessing. It's all, I want you guys to guess. Okay, I want us to guess and then actually, see in reality how good was my guess. That's what I want us to do. Okay, all right. So your guess was 2 channels. Okay. Any other guesses? I'm not commenting on what is correct, what is not correct. One for sending, one for receiving, okay? Bidirectional, okay? Fair enough? So, all of you have some thoughts. Keep that in the buffer of your mind and we'll reflect on that in a bit, okay? So what happens here is, between the system and the memory, that's a memory module, it's called a DIMM, D-I-M-M, okay? Dual inline memory module, alright? A bunch of data lines are there, okay? The blue ones are the data lines, 77 wide, which means that there's 77 lines physically laid out, okay? There's a bunch of address and control lines, okay? And a clock line. This clock is what the synchronous actually means, that everything is clocked. This guy will be forced to move as per the signal actually coming here. Clock is like this, high, low, high, low. This axis is time, just to be clear, not space, okay? So T0 high, T1 low, T0 high, Tx high low, you get the picture, right? So every step is logged onto this clock. This is what is known as the I/O clock, okay? DIMM is dumb, okay? Very few people actually, my guess would be less than 1 in 100 engineers actually know about this. We use things on a daily basis, but we actually do not recognize. There is zero logic on a DIMM, okay? DIMM acts as pure capacitive storage. The nature of the protocol, this bus, is such that this whole storage is exposed out in a certain form. Row address, column address, blah, blah, blah. Some addressing mechanism exists, okay? It's very, very good to go through it, but we'll not go through it right now. You can explore it yourselves. Which means that whatever entity is here is the entity that's actually going to mention that this row, this column, etc. give the data to me. Understood? 77 byte data bus means that at any single point in time, each line is a bit, right? 1, 0. 77 bits of data end up essentially moving in lockstep with the clock. That's why we call it a parallel bus. Remember that thick line in the earlier slide? That thick line represents a parallel bus. It's not a serial bus. Serial bus is, if I were to transfer 8 bits, first I'll send the first bit, then I'll send the second bit, then third, up till 8 bits. So in serial, this thing, can you imagine that latency is going to be higher in serial? Yes. Right? In parallel, 77 bits in one go. Which one should be faster? Which one should be having less latency? Good. Right? So 77 bit wide. This guy is known as a memory controller. Okay? This guy understands the layout of the memory. So when you actually plug the memory into a slot, there's a bunch of lines that I have not shown here, through which information about the internal structure, how many rows and columns exist, etc., are fed to this, and after that it is completely this guy's call. So it may distribute 1 byte, for example, amongst different chips. Okay? So this guy is intelligent, that guy is dumb. Usually, DIMM would essentially come with some spec. DDR4 3200, for example. Okay? Means that DDR4 captures certain electrical timings and stuff like that. 3200 means 3200 million transfers per second. It can do. So 3200 million times a second data is being pushed. You can imagine how much data can be pumped out, correct? What are the lies? Huh? 3200 is the lie? Why? So again, so you've got to reason it out with me. You cannot just talk about a looked up fact. The issue is really staring at us in the face.
3200 is most probably the clock speed, 3200 megahertz.
3200 megahertz. Remember the double data rate? Right? Which means that for every double data rate is essentially at every clock. We send data both at the leading edge when signal rises from 0 to 1 and then at the falling edge 1 to 0. Okay? So which means that in one clock cycle we are sending 2 transfers. Which means that if transfers are at 3200 billion transfers per second, clock speed is going to be 1600 megahertz, just to be clear. But were you saying that that's the lie, that 3200 is a lie? It should be lesser. Why should it be lesser? Sorry? What should be 6400? So if the memory module is 3200, DDR4 3200, this is the clock speed you are saying. So you are saying that the lie that I am saying is DDR4 3200 mein 3200 is actually the clock speed and not the transfer. That sounds like a factual sort of argument. You've got to explain why do you feel that that should be the clock then.
That is the nomenclature.
That is not the nomenclature. Just to be clear, you could be right. You could be right. But here we are arguing because you are not using reasoning. You are just saying, no, I disagree. That is actually because of something that you have read, right? Okay, I disagree.
So basically 3200 is the clock speed because if it was the transfer rate, like people don't know like double it, the data is being transferred 2 times. Okay.
Mm-hmm.
And one clock.
Understood. I get what you're saying. You're saying this should be the clock speed. I am just saying it should be the transfer rate because when people are calculating the actual raw speed of the memory module that they are putting in, it's easier to derive from the transfer rate instead of the clock speed. One less calculation to do. 2x ends up getting eliminated. Okay, I got reason to believe that this is actually transfer rate and not clock frequency. Any other potential candidates for lies?
Why are they 7790? Why is the specific number?
Why is that specific number?
Yes, if let's say we have a different type of RAM, then won't it be difficult? Won't there be some other hurdles of like how many chips are there in the RAM? So that
Good way of thinking. Good way of thinking. Anybody wants to sort of add on to that? 77 does feel odd. Feel odd. Multiple of 8. Multiple of 8, multiple of 2. Yeah, no, he's correct. It should be actually multiple of 8.
Yes.
Right? Why? Yeah. When in our software, like what is the unit of data that we work with? Byte. Sometimes we need to look at individual bits, yes, but we are always working at a byte, right? 77 byte data bus feels odd, right?
Yes.
So yes, that is a lie. And the reasoning is that what he said, that we get some number of bytes and some leftover bits. What do I do with those bits? Like there's no program where I will be dealing with those bits. It just feels stupid. It means that I'm sending some extra data which cannot be used. Simple reason, right? Okay, good. Sorry? How 70? A good question. Yeah, I was hoping somebody would ask that. 64 is the baseline. Okay, that many number of data bits we actually do transfer. 72 is if there is ECC. ECC is error correction. Okay, if there is ECC in the memory module, additional 8 bits of data end up being transferred. Okay, so really depends upon if your DIMM supports ECC and if your CPU supports ECC. Why do we need ECC? If we talk about there is some support of 8 extra bits, it's got to have a reason, right? I'm wasting data lines onto something. I could have easily sent across 72 bits of data, but instead I'm sending 64 bits of data and 8 bits of something. That something is what I'm referring to as ECC. There should be a reason. Why? Why would that be needed? Food for thought. Okay, you guys investigate and figure out. Nobody? Computer builders here? No? If some bits are not working, that's a valid possibility. What else? Cosmic rays, have you guys heard of it? Yes. Right? Yeah, it's sort of going through all of it. It actually ends up hitting our DNA every now and then as well. Right? It's just that the probability of it inverting some gene causing cancer is just very, very low. Okay? So, if you leave a non-ECC machine running for a long enough time, at some point in time it will get corrupted. Murphy's law, if something has a probability of happening, given enough time, it will happen. Okay? So if there are cosmic, so like very, very, tiny atomic particles sort of hitting, every now and then they are going to flip a bit. Okay? ECC helps take care of it. But then we'll get going deeper into it is because it's not a communications theory class, so we'll skip it. Okay? That's what ECC is for. Okay? Which also means that it's not just during storage. It could also be during transfer that ECC might be needed. Then another question comes up. Inside the CPU, would there be ECC? Yes or no, I don't know. I'm just laying down the questions that come up in my mind. I want to get you guys to get in the habit of thinking questions. Remember our principle? Thinking questions. Okay, so the moment I've explained ECC to you, a great student here is going to think about all the different places in which, why have I not heard about ECC inside a CPU till now? Maybe I should look it up. Okay, does my GPU have ECC? Maybe I should look it up. Okay, what about my display? What about my storage? And suddenly you start thinking about all of these possibilities, right? Each one of these possibilities is going to push you towards learning something new. Alright, so, okay, so this is what, at 3200 million transfers per second, 64-bit wide, let's skip ECC for now, 64-bit wide, even in ECC 64 bits of data only 64 bits are getting sent, right? So we've got 3200 million transfers happening in parallel. This is a parallel bus. Okay? It's happening in lockstep. When there is a high, all of these things are getting sent, going low, another transferred. So double data pumping. So 3200 million transfers times 8 bytes. That gives us the bandwidth. That is how, so every time you see this, can you derive the bandwidth now? Right? Why am I not hearing a very clear yes? Not sure. 3200 million transfers per second are happening in parallel across 64 lines. 64 lines translates into 64 bits, which translates into 8 bytes, which means that every transfer, how many bytes am I sending? 8, right? Which means that if I am sending 3200 million transfers per second, how many bytes per second am I sending? 8 times 3200 million, which 3200 million translates to 3.2 giga transfers per second, times 8, 25.6. Make sense? Alright, so by the way, DDR5 includes on-die ECC. So in a if this were DDR5 stick, on the die itself you have ECC, Food for thought. Would the link require ECC or not? Or can things get corrupted during the link? So if the question is, no matter how many transfers per second, if I can just, why should I not have like 128 bit? Why? Cost. Okay, that is one. What else? Space, makes sense. But that is double data pumping, we've already talked about it. Okay, we'll come to this in a bit about why not more. Latency. These DIMMs store information as capacitive charges. Okay, there's a charging time. Every time you write, charge. For X amount of time, some current will have to flow through for it to charge, then discharge, right? So every time a read happens, there is discharge. And because there is discharge, every time we are reading, remember that a write will have to happen again so that it maintains charge. That is what is known as DRAM refresh. So the higher the capacity of DRAM in your laptop, that much more demanding it's going to be on your battery. On your phone, also, DRAM eats up battery, okay? Anyhow, latency is 50 nanosecond, as we discussed in the previous thing. And again, you are having to trust me right now, right? Because it is capacitive storage, okay? So if it is 50 nanosecond, a command goes in, when do I get data back? 50 nanosecond later, right? What is the expected throughput I should get? 50 nanosecond, I got how many bytes? 8 bytes, right? Okay? So which means in 100 nanosecond, so I got the byte, then I sent the next request. Okay? In 100 nanosecond, I got 16 bytes, right? So in 1000 nanosecond, I got 160, right? So which means in 1 microsecond, I got 160 bytes. Into 10 raised to 6, right? So 160 million bytes I would have gotten in 1 second, which means my bandwidth is 160 million bytes per second, megabytes per second, right? But we talked about bandwidth as this. What's happening? My data lines, because they are operating at 3200 million transfers per second, they have the ability to send it as many times. But what is the bloody, slow poke and all of this? The latency. Every time I send a request to read, it takes me 50 nanoseconds. There's no way I can avoid it because it is capacitive, it's limited by physics, right? Amdahl's law strikes again. We are limited by the slowest poke, right? So despite the fact that we have the ability, despite the fact that our bandwidth is 25.6, the throughput that we can expect is 150, kitna tha apna? 150 megabyte per second. 160 megabyte per second. Yeah. Something seems very wrong. Where have we gone wrong? Is that really the bandwidth that you expect from your memory? Something is very wrong. So we are missing something. We talked about this just for the third time. How can we hide latency? Huh? Increasing throughput. Obviously, we'll have to design our system in a way that makes real good use of that throughput. But if we can figure out a way to drive more throughput, use the throughput a little more effectively, right? We can minimize the effective latency. We can hide the latency, correct? Yeah.
Why are some of the lines red, blue, and green?
Oh, that's just we classify. This is clock. Okay, just classifying data separately from address and control, and that. Yeah. So how can we remember that stall guy? A request came in, processing happened, response came out. Okay. That's the reason why we are getting choked on the Amdahl's law. That this 15 nanosecond is bothering us, right?
So we need a code like that.
Yeah, so maybe one of the things that we could do is keep on sending requests, right? We keep on sending requests instead of having to wait for the response, keep on sending requests. So if my first request goes in now, and the response comes back 15 nanosecond later, what I will do is send the first request, 1 nanosecond later let me send the second request. Alright? So I'll pile it up with 50 requests so that I'm continuously getting stuff, correct? That is one way. This is what we did in the stall. This is, yeah.
Would that lead to vulnerabilities?
Wouldn't that?
Lead to, if the information we are sending is dependent on each other,
Yeah.
and one of the requests supposedly fails,
Yes.
then what would happen?
That's a good example. That's a good point. Okay, and that is known as a hazard. If the way that you were pumping, if your requests have some dependency in them, you cannot pipeline those. This process is called pipelining. Okay, it shows up in CPU, it shows up in DRAM, GPU, all the different places in your operating system. Okay, pipelining is a very standard way to hide latency by throughput. Okay, real question is pipelining suffers from data hazards. Okay, so that is one of the things. But for the timing, let's park it for now. Let's assume that there is no hazard. What is the issue with pipelining? Can we pipeline in DRAM here in the way that I was describing? Remember, DRAM was dumb. Okay? Now I cannot detail it out without getting into some of how DRAM internally functions. But the point is, some of these control lines, memory controller needs to keep it on for a particular read to complete. So I cannot send another request in, just like that. I need some amount of data to start flowing before I can send the next thing in. I cannot do it before that. Just, this is one thing I'm requesting you to take it on a face value for now, okay? Because it just will take up a lot of time to explain DRAM internal structure, okay? So instead what we do, for every request, what if instead of serving 8 bytes, I send a burst? You ask for 8, I'll give you 32. Okay? This is known as burst. And by the time those 32 ka time khatam ho raha hai, by the time those 32 are being transferred, just at the end of it, I switch on just the adjacent cell. So in memory structure, the way, because of the charging and discharging, a large part of that time is actually known as a pre-charge step. Sometime earlier we were talking about latency being 13 nanosecond or something, or 15 nanosecond, right? Yeah, 15 nanosecond. That latency, DRAM read, is actually a multi-stage process. Some of the earlier stages actually take up a bulk, a fair amount of time. Once those steps have been done, sequentially I can keep firing a bunch of additional read requests up to a limit. Okay? All of those things I can send it out as a burst. Alright? So that burst, if we call it as BL8, burst length 8, if we are sending, for every request we are sending 8 such bursts. By the time those 8 are done, my next similar address is already covered, which requires just 15 nanoseconds extra. Got it? So that is how we actually take care of hiding latency. All of this is one channel. Okay? So alright. Memory hierarchy. Because memory is so bloody slow, what do we have? So this is my CPU. This is bloody slow. We already know this, right? How does CPU do its calculations? It has something known as registers. Okay? These are like right there at the center of the processing area. Okay? Each register can be read in one clock cycle of the It's like highly tightly clogged to the CPU core. All right, bandwidth is more than 1 terabyte per second. Super duper high. Okay. Next guy, what do we do? L1 cache. It is usually dedicated to the core. Much smaller in size. Next is L2, next is L3, and if things are not found in L3, things are fetched. Okay? So the way it happens is, the code looks up first in L1. If it is not found in L1, L2, L3, memory controller, and then back. Make sense? Okay?
When does it check through the register?
Sorry?
When does it check through the register?
So all of your instructions, when you do A plus B, it translates into what is known as machine code, right? Machine code is always either linked with processing something, a data that is already available in the register, ya fir it is doing a load or a store. Load is fetch from memory, put it in the register so that the next instruction can process it in the register. Okay, store is let me write it back to the memory. Some data was already in the register, let me put it back in the memory. Okay, so L1 lookup is 5 cycles. So L1 does have some cost. If for a 3 gigahertz CPU, one cycle would be how much time? 1 gigahertz would be how much? 1 nanosecond, right? Giga, nano, that's how I think. So 3 gigahertz would be 0.3 nanosecond, 1/3 of a nanosecond, right? So register lookup 0.3 nanosecond, L1 is 1.5 nanosecond in a 3 gigahertz. Remember, somebody was asking a question about overclocking. If you increase the clock speed of the CPU, all of the times get reduced, okay, at the cost of higher energy. L2, 15 cycles. L3, 75 cycles, okay. I like to remember this as 535, okay. Register 1 cycle because ultimately everything needs to be clocked to the CPU clock, okay. It's 1 cycle, like hardwired. 5 times this is 3 times this, 5 times this. So I remember it as 535. 5x, 3x, 5x of the previous one. Okay, just sharing one way to remember. Question: why are L1, L2, L3 so fast? And if it is so fast, why don't we just use, run with only L1, L2, L3? Expensive? Why is it expensive? Or did you just read it up on the internet? Of course you read it up on the internet, right? I also did that. Yeah. So, but the real question is, at some point in time we have to think about why is it actually more expensive? Why is it faster? Flip-flops. Good point. It stores information. It just stores information as a logic circuit using only transistors. That's what he means by flip-flop. That circuitry is called flip-flop. It uses 6 transistors. Okay. All of these are what are known as SRAMs, not DRAMs. SRAM, static RAM. When you do a read, there's nothing that needs to be refreshed. In case of dynamic RAM, things need to, because you discharge the capacitor. Because this is pure logic circuit, it uses only transistors. There's no charging, discharging. Technically it's happening, but of a very different kind. Okay. Whereas DRAM was capacitive. Capacitors are slow. Okay. So these SRAM, going back to the flip-flop, uses 6 transistors. DRAM uses 1 transistor, 1 capacitor for 1 bit. We call it 1T, 1C. SRAMs are called 6T. There are better circuits also sometimes, but 6T. Okay, that's the reason why it's expensive. Okay, so for the same size, you can store much lesser. You can, for the same physical size, you can store much lesser in case of SRAM. Okay. Why is L1, L2, L3 being measured in cycles, whereas DRAM is being measured in nanoseconds? Good point. So we say that as clock domains are different, right? All of this is logic circuit. Remember L1, L2, L3 are logic. Sometimes L3 can be implemented with some DRAM also, just to be clear, but usually it's all logic circuit. Logic circuits are running as per clock, pure transistors. They can switch very fast. Capacitive cannot switch fast. There's no switching in capacitive. It's charge, discharge. So the clock domains are very different. In fact, I'll skip that piece of information for now. Yeah. L1, L2, L3 are fast. So programs that end up relying on data that is very small amount of data that is very frequently accessed would be in this thing. Programs that need to access DRAM all the time would be super duper slow. Okay? There is a puzzle that I had given quite some time back. Any of the staff here who might have attempted it? It's about something called columnar store. Columnar storage. It's a database concept. Okay? I'll share that's an assignment. You can actually see why understanding this information allows you to write better software if you were to try out that puzzle. Okay? Things become very slow if you are accessing DRAM. Alright? This is also why GC languages, GC is garbage collected languages, they can be quite slow. Okay? The issue is not with the language syntax per se. The issue is with the fact that if you garbage collected means that your memory is usually quite spread out over a wide space in heap. L1, L2, L3 work on recency and locality. Remember that DRAM sends out close by data in a burst. That's data that is close by, just adjacent to the line. Okay. For every read that we do, it sends me 8, a total of 8 times more information. Right. So the next nearby access becomes much cheaper. Okay. That information is actually very useful when you are writing some software. All right. This is usually 2 channels. Somebody was talking about channels. This is what a channel is. Here and this we can actually do in parallel. Higher throughput gives us more throughput. We refer to this as 128-bit wide bus. The moment we've got 264-bit channels, we refer to this as 128-bit wide memory. Okay. Did any of you do the Apple M1 pre-read? What was the memory throughput of memory bandwidth of M1? Yaad nahi hai. What was the reasons given for things actually being fast in M1?
Because GPU, everything is inside the chip itself.
Inside the chip itself and accessing what is known as unified memory. Alright? Unified memory is possible only if you have very wide memory bus. Okay? And that gets implemented by multiple 64-bit wide buses. Each one of these is called a channel. Okay? Yeah, 200 gigabytes, right? 200 or, yeah. Okay, so that is implemented by having multiple such channels. Again, throughput helps us hide latency. So a CPU that is running with only one channel will see the effect of memory latency far more than a CPU that is actually having multiple channels, okay? Cache internally is actually split up into cache lines, usually of a 64-byte length or 128-byte. Remember when we were talking about burst, BL8 was giving us 8 transfers for every request. 8 transfer over an 8-byte wide bus is 64 bytes. So do you see how this is linking up with cache line? So burst length actually correlates very strongly to the cache line. When we are making a request, we actually get more than what we asked for, and that whole thing is actually pumped up in a cache line. Okay, so say for example we ask for this data, the rest of the data we get for free, which is why nearby accesses become super fast. Multiple processors. Remember, memory controller is on the CPU. right? We've been talking about it, okay? DIMMs are dumb, all right? Multiprocessor CPU, CPU 0, CPU 1, okay? Because memory controller is on the CPU, each one of them will have its own distinct connection, okay? Say for example, so which means that if there's a process running here, it will need to be able to access memory here, right? Because it's the same system where we are running multiple CPUs, correct? Which means that there has to be some interconnect between these two, right? That is what is Intel calls it UPI, AMD calls it XGMI. The more important thing is a process running here on CPU 0, when it is accessing the memory, the local memory, it's going to be fast, 50 nanosecond. Throughput hidden latency will come down to about 15 nanosecond, okay? It's this fast. But if for any reason this guy ends up accessing the memory there, it's going to be slow, 100 plus nanosecond, okay? Which is why when in server space, when you are dealing with multi-processor servers, we call this as NUMA awareness. Memory, you need to write programs which is usually accessing memory that is local. Your OS scheduler is aware about it. When it schedules a process, the first time that the process got scheduled, it will usually make sure that whenever you are calling for more memory, the OS is providing memory from the local guy, not the other guy. But once in a while, when dealing with large memory, you would find yourself, why is my memory slow? And then you will discover about NUMA and then you would remember this session. All right. This is what actually a die shot looks like. These are cores. There's actually just like that interconnect between processors, there's an interconnect between cores. This is called a ring bus in case of Intel, okay? So here would be your PCIe Express physical links, your memory links, your memory controller is sitting here. PCI Express, let's quickly come to this and then we should be done. Each lane is actually composed of this one guy sending, one guy receiving, okay? 16 giga transfers per second, PCI 5 doubles it up. This we've already talked about. PCI Express, it's a serial link, remember, okay? What we have is we have these additional layers which are actually not too different from your network stack. As you know, at some point in time you guys will learn more about that. Just remember that you'd seen a diagram, something similar to it, okay? So these patterns are actually very common and reusable, okay? All of this communication is packetized, which is why, packetized as in information goes in fixed units, okay? Which is why your chipset can deal with oversubscription. If something is actually sending more data, it can buffer that data locally and send it when its upstream becomes free. Make sense? Okay? Interesting thing is exactly this happens in network, in your internet network. Okay? So very, very reusable concepts. Okay? Higher latency because this is a serial link. Throughput hides a lot of that latency though. SATA, NVMe, I'll skip this, we've taken up a lot of time. Important thing is a lot of people confuse that, think that SATA and NVMe are a kind of disk types. That is not true. Storage medium, magnetic, optical, NAND, flash, those things are different. SATA or NVMe is the protocol that the disk controller uses to actually talk to the operating system. Okay? Speed is governed by the storage medium. For example, NAND flash would be faster than the protocol. An SSD is composed of these storage chips, right? It can be fronted with a SATA. SATA is the protocol that it is using to talk, okay? Or it can be fronted with NVMe. SATA actually has 32 deep command queue. Pipelining we were talking about, requests keep on coming in, I will process them in some form, okay? Beyond 32, you cannot send to SATA. So it cannot be processing more than 32 commands. NVMe, which means that even though you had sufficient capacity if you were using an SSD, if it is fronted by a SATA, you would be bottlenecked on the bus, on the SATA bus. Whereas in case of NVMe, it's actually very, very deep queues, which means that you would usually be choked by the actual storage medium, all right? This is a summary of, once you start looking at these things, when you start writing software, one of the best things to bear in mind is, stop distinguishing between disk versus network versus something else. Start thinking about distances, latency. This is very close, cache is L1 is very close, L3 is a bit far, DRAM, it's in Mysore, okay? And throughput. Do I have a two-way highway to Mysore, or do we have a 10-lane highway to Mysore? Okay, you start thinking about it like that, and everything gets reduced down to these two concepts. Okay, so yeah, we covered Amdahl's law. Performance is about overall latency. Main memory is damn slow. I/O is way, way slower. Serial lines rule everywhere except memory. And all of system design is about hidden latency via throughput. It's true for hardware, true for software. All right. I'm very sorry. I've taken a class after a very long time, so I didn't time things very well. The amount of coverage that we did usually takes a semester. Okay. So I'm also very sorry for dumping all of this in one go. My personal experience is that these are not very difficult concepts. And you guys are smart enough, which means that I have the ability to dump all of this in one go. And hopefully those distilled down core principles would stick around, even if the facts don't. Facts will keep on charging and discharging from your mind, but hopefully the principles stick. All right. Any questions, or just it's already quite hot in here. Any questions? Why the GPU's connection is slow to the CPU? It's because it's on the PCI bus. PCI bus electrically, see, every time we are doing a serial transmission, right? Latency is going to be measured in terms of how effectively you can transfer X amount of information. Okay. Serial buses, you remember that stacking I had shown? Your serial buses mean you're sending things one bit, next bit, next bit, next bit, right? Those bits, there's something in there on the receiving side which is received one bit, okay, park. Second bit, park. Third bit, park. Until I have like 8 bits or 64 bits, whatever, and then send it to the next layer. So latency naturally increases. And the reason why we actually didn't talk about, the reason why serial buses rule is because when we are sending parallel buses, you remember speed of light? Speed of signaling rather in this case. In 1 nanosecond, how much distance were we traveling? 15 centimeters, okay? Which means that as we increase the frequency, the amount of distance that we cover in the same unit of time keeps on reducing. If we were switching at 10 gigahertz, it means that the unit of time is 0.1 nanosecond, correct? In 0.1 nanosecond, we'll cover 1.5 centimeter. So when you have a 64-bit wide bus, that's what 64 wires have been laid out, right? Slightest bit of gap in between them. Remember, all of them are supposed to be going in one shot. Slightest gap, one is slightly longer than the other. Your signals are off. Why? Because you are supposed to be sending it in lockstep, right? That's the reason why in motherboard sometimes you would see those traces having some designs. It's not like somebody wanting to be creative, let me draw a flower. It's actually because they want to make sure that the trace lengths add up to the same thing. 64-bit wide bus when it is turning, outer one is longer. So they will draw some extra curves on the first one. So that's the reason number one, why parallel buses are less popular. Another reason is that the higher the frequency, that much more crosstalk. If you remember your basic physics, electricity and magnetism classes from physics, you would remember that higher the frequency, that much more sort of capacitive crosstalk that you would actually start seeing, right? So you cannot increase the frequency beyond a certain limit in parallel buses. In serial buses, on the other hand, For every serial link, you have 2 lines going, and they tend to be self-clocking in nature. You can read up more about it. That was parallel versus serial. Yeah.
When we are writing programs which use multiple threads,
Yeah.
what if like many of our processors try to read the same memory, and when it's in DDR RAM, and what if it was already like the time it takes to recharge it back? What if we read it and it's empty? So won't we misunderstand that?
Which is why you cannot issue the next read until it has been refreshed. Okay?
So then it's not like it will have a.
It has a, which is another, so read process, interestingly, is read plus write, which is very unintuitive, but in DRAM, every read is read plus write. Okay? Cool. I hope that some of this was helpful. Our next this thing would be inside the GPU, where we'll go deeper into GPU and how it's different from CPU, and we'll be using a lot of the concepts that we picked from here. So I'm hoping that you would remember at least some of what it covered. All right. Thank you so much.